start the afternoon session with a brand new speaker, Xavier, Leroy, who comes from INRIA Paris-Rocanfouze, and who will talk about the celebrated concept project which has been mentioned many times before his arrival.
Okay, well, thank you, Pierre-Louis. So, good afternoon, everyone. Can you hear me? All right. So indeed, I'm going to talk about mechanized verification of compilers and compiler-like programs. So, program transformations or static analysis of programs. And I will be using the Coq-proof assistant throughout. But let me start with a little prologue. So this is really all about operational semantics and how we mechanize them on machine and how we apply them. So what's the purpose? So probably everyone here knows about that, but well, basically we'd like mathematically precise answers to the question, what does this program do exactly? And well, for simple programs, it's kind of obvious, but here are some examples where it's not so obvious. So this is legal C code, okay, and it computes something useful, but you won't guess. Maybe the shape of the program can give you a hint. So it actually computes square roots in arbitrary precision, okay. And of course, this one is a joke. It's from the obfuscated C code contest, where people try to write the ugliest possible C programs. But here is one that is not a joke. So if you look at it, so this is a decompressor for a simple compression scheme called run length encoding. So basically, you have a special code meaning n repetitions of the following character. And so if you look at it superficially, basically you're reading a character. If it is a special character, then you read a length and a character, and you emit n copies of that character. Otherwise, you emit the original character, and you do that until end of file. So it looks like a perfectly regular I/O loop, except now if you look at those macros, CR return and CR finish, and which are really weird. And it takes a while to realize that actually this is a coroutine. Okay, so every time it's about to produce a character in the output, it returns it to its caller, but it remembers where it left. So the next time the function is invoked, it will produce one more character of output, and so on and so forth. So this is really clever, but it's kind of hard to convince yourself that it does what it should. And this is not a joke. I mean, it's part of PuTTY, which is an SSH client for Windows, SSH being the secure shell, so a highly secure protocol to connect to remote machines. And so basically, any mistake in that means a security hole, right? All right. So, as I said, why indulge in formal semantics? Well, because it's fun, but also anytime English prose is not enough. In particular, the language standards, which are often hundreds of pages of English or standardese, and still fail to achieve the required precision in some cases. One step further, it is a prerequisite to formal program verification. Whether you're doing program proof, deductive program proof, model checking, static analysis, abstract interpretation, and so on, you need a really precise definition of the semantics of the programs that you are analyzing or verifying. And still one step further, and this is really the topic of my lecture, is a prerequisite to building reliable meta-programs. So meta-programs being programs that work over other programs. They take programs as input, they produce transform programs as outputs. And compilers are a typical example, but there's all sorts of code generators, from modeling languages to executable languages, for instance. Program verification tools, like these, the tools that help you do those kind of verifications, type checkers in statically typed languages, and so on and so forth. And so now let me ask similar questions, but not about individual programs now, but about program transformations, like you can find in compilers. So this is a program transformation that performed by SIL. So SIL is a C intermediate language, I think. So it's a camel library to help implement program transformations and program analysis for C. So it's been written by George Nekula and his colleagues at UCB, and it's a really fine piece of software. And as basically SIL parses C code and then puts it in an intermediate form that is basically a subset of C, a simpler subset of C that is easier to work with. And one of the transformations it does is pull side effects out of expressions. So in C, this assignment can occur within an expression because an assignment is not a statement, it's an operator that has a value, which is, roughly speaking, the value being assigned. And well, but that kind of code, so basically what this function does, it takes by reference a pointer to a list, and then it sets the tail to null, and it returns a result of this assignment, which is null. And so SIL version 1.3.6 transforms this to the code on the right, where first you assign, okay, null into that location, and then you return the content of that location. So that should be perfectly equivalent, right? You're assigning into something and then returning something. However, the code on the right can crash in some cases, while the code on the left cannot. And the problem is if you feed that function a very circular list, okay, so basically this is a list that points to itself, and then you take for P, you take the address of that tail field, and now what happens is that when you do this assignment, you put null not only in this tail field, but also in P itself, because they are the same, okay, you have a loop. And so now when you do star P here, you crash, okay, and that's a fairly subtle point. Well, it was fixed in SIL 1.3.7, but still, that's worrisome. And one last example. So this is an example of aggressive optimization. So this is a simple C source code that computes a dot product of two vectors of floating point numbers. And as you see, it's really the textbook formula. Okay, you're summing the products AI times BI and returning that. So really simple code, easy to see that it computes the dot product. And so a few years ago when I started working on compiler verification, I took that code and compiled it with a good compiler. So it was the Digital Unix Alpha compiler, a good compiler from the 90s, not state of the art. And with all optimizations, and then I looked at the assembly code, and I couldn't make any sense out of it. It was huge. Then I spent half an hour decompiling back the assembly code to C, maybe hoping that it would be clearer. And I got this. So this is a C code equivalent to what the compiler did with that poor little function. And it doesn't make any sense. And if you look at it more closely, you see a loop here, okay? So that's, well, we had a loop originally, we have a loop now, so that's good. But the loop is very different, okay? First of all, it computes things by, well, it's been unrolled by a factor of 4. So each iteration of this is going to do 4 multiplications, 4 additions, and so on. Then it's been software pipelined, which means that at one iteration is doing the addition for that iteration, the multiplications for the next iteration, and the loads for the iteration after, okay? So that gives more time for the processor to compute all that and fetch data. But it introduces lots of difficulties because those software pipelines, well, they need to be primed. So the first iteration is special. Then they need to be drained in the end, so the last iterations are special. And so some of this compensation code here and there does just this. And then there's a case where the loop, the number of elements is less than 4, or maybe 8, which needs to be treated specially. And then there's the case where the number of elements is not a multiple of 4. Okay, and that also needs to be treated specially. And that's why there are so many special cases here and there and there and there. So in the end, we get code that runs twice as fast, or maybe 3 times as fast as the naive code that you could have written by hand. So that's wonderful. But it's still very unclear whether it computes dot product or not. Okay. All right. So, well, this goes without saying in this audience, but of course we are going to use proof assistance to, well, formalize those semantics for more or less realistic languages, and then reason about program transformations and program analyses. We will use Coq, and that's fortunate for you and me, because that's the system I am most familiar with, but there are many others that are pretty good too. And there's a really good fit between proof assistance and mechanized semantics, because, well, formal semantics for realistic languages, they are large but shallow formal systems. Okay, many cases but no deep mathematics, and computers are better than humans at working with that. So basically, I swear a couple of years ago that I no longer want to see any paper that says the proofs of the remaining 18 cases are similar. I'd much rather see in papers that pointer to a mechanical verification. Okay, so in this lecture, we're going to use the Coq proof assistant and formalize some representative program transformations and a bit of static analysis and prove their correctness. So we'll have to define what that means exactly. And in passing, we will introduce some semantic tools that we need for this effort. So it's mostly operational semantics. So we will build on Benjamin Pierce's lectures. So I'm going to use his IMP language, small imperative language, as a starting point, and some of the semantics that he showed. And then we will introduce some additional tools along the way. So the lecture material is available on my webpage. It is linked from the summer school pages. So there you can find the Coq development. So there's a source archive. It contains a copy of Software Foundations for your convenience. There's also an HTML view. And there's a copy of the slides too. All right, so, and this is the outline. So we will start by a very simple compiler from IMP to a stack-based virtual machine. So nothing too ambitious, but it sets the stage, and we will do our first compiler proofs with that. And then we will think a little what it means for a compiler to be correct, to be semantics preserving. And we see that we need a little more in the way of semantics. So we'll have a look at the various styles: small step, big step, co-inductive big step, which is for to capture divergence, definitional interpreters, and even a simple form of denotational semantics. And armed with this, we will revisit that proof of the IMP to virtual machine compiler. And then we'll do a little bit of program optimization and static analysis. So the optimization that we look at is called dead code elimination, and it's based on a static analysis called liveness analysis. So we will define and reason about all that, and extend it to register allocation, which is absolutely crucial optimization for all modern compilers. And then we'll move to a more generic view of static analysis based on abstract interpretation. So do not be afraid. That will be abstract interpretation explained in simple, low-level terms. And we'll finish, if time permits, with well, an overview of what it takes to scale those techniques to basically a compiler for the C programming language in all its horror. And that's this CompCert-C project that Pierre-Louis mentioned, and some other teachers too. Okay, so let's get started. with a short reminder on the imp language that you saw in Benjamin Pierce's lecture. So it's basically a very simple imperative language that has a structured control flow. So there are commands like skip, that does nothing, assignment of an expression to a variable, the sequence of two statements, conditional, if some Boolean condition, then do C1, else do C2, and a while loop. While the Boolean condition B is true, do the command C. So at the level of arithmetic expression, so we have only one data type, which is integers. Arithmetic expression, well, we have constants, variables, and sum, difference, and product of two expressions. And for Boolean expressions, so we can test for equality or less than or equal between two expressions. And we can also take Boolean negation or Boolean conjunction. Okay, so nice, small language that fits on a slide. And so in his lectures, I think, so Benjamin defined an operational semantics for imp. So there are 3 layers: arithmetic expressions, Boolean expressions, and commands. So for arithmetic expressions, it's basically a function, a val, that takes an expression a state or store that gives values to variables, and then produces the corresponding number. Okay. And so stop me if you need more. Yeah, if we need to go over this in more details. Likewise for Boolean expressions, so B eval takes a state, a Boolean expression, and returns true or false, its truth value. And then for commands, there's an evaluation predicate that says command C started in state ST, terminates in final state ST prime. Okay, and it is defined in so-called big step operational style. I'll come back to that later. Okay, so we have pretty good semantics for imp. And now we'd like to execute imp programs. So there are basically 3 choices when you want to execute a programming language. The simplest one is interpretation. So you just represent the program by an abstract syntax tree, and then you have an interpreter, separate program, that traverses this tree and executes the corresponding commands. So that's easy. That's a bit slow sometimes. So at the other end of the spectrum, you have compilation to native code. So before execution, the program is translated to a sequence of machine instructions. Okay, and those instructions are those of a real microprocessor and can be executed in hardware at very high speed. And we are going to do something in between, which is compilation to a virtual machine or abstract machine, where again we are going to translate the program to a sequence of instructions, but those instructions are not those of the x86 processor. Okay, they are those of a virtual machine. They are chosen close to the basic operation of the source language, so that compilation is easier than going all the way to x86 assembly code, for instance. And then what do we gain by doing so? Well, we can then write an interpreter for the virtual machine, and those interpreters are typically faster, maybe 5 times faster than interpreters operating over abstract syntax tree, because some of the decisions have been already pre-computed and maybe even optimized by the compiler. Or you could also use virtual machine code just as an intermediate language and further translate it to machine code. That's typically what Java or C# implementations do. Okay. So let's have a look at a virtual machine for imp. It's going to be a very simple stack-based machine. It has 4 components. So there's a code, C, which is a list of instructions. So we'll see what instructions we have pretty soon. And then the state is in 3 components. There's a program counter, which is an integer that gives the position of the currently executing instruction in C. Then there's a store, as in the operational semantics, which maps variable names to their current integer values. And there is a stack, so just a list of integer values that we will use to store intermediate results